Good afternoon to everyone. I am Nadine Al-Kosafi, Marketing Product Manager of COLDFORM. It is my pleasure to welcome you to our webinar dedicated to the improvement of fasteners quality and durability using COLDFORM simulation software. At the end of the presentation, my colleague Max Binago will join me for the question and answer session. Now the camera will be turned off and it will be back during our conclusions. Before we start, just a few words about the GoToWebinar platform and how to operate the control panel. You can use the orange arrow to minimize the control panel to the right. By default, the microphone will be turned off for all the participants. At any time during the presentation, feel free to type your questions. During the question and answer session, I will get back to you and answer these questions. This is the outline of the webinar. First, I will start with a general overview on the fastening solution. Then I will present the benefit brought by the simulation and the fastener forming applications. An example of the manufacturing process of a bolt will be presented. We will see how to take advantage of COLDFORM to increase fastening die life, and how to use the integrated optimization model on a screw forming case. Finally, we will see the conclusions. Choosing the right fastening solution means a challenge on the engineering side. Numerical simulation can be used as a tool to reduce the production cost and to increase the performance. Numerical simulation can be used as well to investigate which assembly technique to use. The fastening solution must address high-level functions such as durability, weather tightness, aesthetics, and structural performance. COLDFORM software can be used to guarantee these functions. Let's talk a little bit about what we can expect from finite element simulation and the two types of analysis: process analysis and product analysis. For process analysis, the focus will be given on the feasibility of the process. Is the part correctly forged? Is there any defect on the final part? What are the influence of the process parameters? Thanks to the process analysis, the simulation allows also to check the dimensional aspect and to optimize the forming process. For product analysis, we will test the part performance under in-service conditions. Let's start with the benefits of the simulation applied to the fasteners forming. For material, the software offers several manners to define it. COLDFORM software includes an exhaustive material database with more than 250 references, specifically characterized for cold forming processes. As well, it is possible from the grade specification given from your material supplier, it is possible to create your own material file. Then here, if you have the grade specification given by your own supplier, you can use the rolled rheology generator tool integrated in the software to create your material file. You need to enter the ultimate strength, the yield strength, and the elongation and the break. By defining these parameters, the rheology generator tool will create the material file. As well, the software is also compatible with external material tools such as GMAT Pro and Total Material. You may have questions concerning the wire shearing to length operation which precedes the shaping. Then in this animation, we see the shearing operation. This operation can be modeled and the sheared surface can be predicted accurately thanks to the adaptive remeshing technique developed in the software. To the right here, we see the video of the remeshing adapted on the sheared surface. It is possible to measure the force, here we see the force needed to make the shearing operation. Here the force has been multiplied by 2 since a symmetry plan has been used in this simulation. This case of Hex-Stark's screw was provided by Miguel Altuna Institute of Spain. For fasteners, we typically have steps at the beginning that can be simulated in 2D, and other steps that can be simulated in 3D, for example, the reduction of the hexagonal head, the heading, and the forward extrusion. Between the 2D and the 3D cases, we can define a transition that will allow the transfer of the geometry from 2D to 3D. We can check here and see that the results are in very good agreement with the reality. And in the gray, we have the reality geometries. And here we have the numerical results. Results are in very good agreement. Through this example, we will focus on the results analysis. We will see that we have several features that save your time and make your work more efficient. At the end, we will have a look on the results that must be analyzed for this type of application. Depending on what you are interested in, feasibility studies, forging cycle design, tooling lifetime optimization, forging defects detection, quick tools are available for a complete study of the results in COLDFORM software. You can easily display scalar results for parts such as shape feeling, internal stresses, defect, and the part hardness. For the dies, it is possible to determine the abrasion wear, internal stresses, and the fatigue. For the equipment, you can predict the press tonnage needed to create the part. As you can see in this video on the right side, an animation with all stations can be played to see the entire process. Results can be displayed in several windows for more efficiency. Here, for example, we divide the graphical view on 4 windows. And it is possible to divide the graphical view up to 9 and use up to 9 windows. It is very useful to use these windows for comparison between project results. It is possible then to display several results at the same time. As well, it is possible to synchronize the view, the appearance, the results, and the states. Please note as well that it is possible to save the workspace. When saving the workspace, we will save the draw style, the angle view, the scalar, the mirroring. The new result analysis will be faster by saving your workspace and reopen it when needed. The predefined curves can be used to create specific plot. For example, for the dies, it is possible to plot the force versus time. Here, for example, we see the plot that has been overlaid on the graphical view. You must select the source and the parameter of the curve. And it is possible then to display easily the curves. It is possible to make overlay on the graphical view. These curves are available for multi-curve plot application. They are efficient and make results analysis faster. If you want to overcome dimensional defect due to elastic unload, it is possible to measure the displacement due to the elastic unload. The last increment of COLDFORM corresponds to the elastic unload prediction. The graphical view is divided on 2 windows. On the left window, we display the increment corresponding to the elastic unload, and on the right, the last forming increment. As we see here, the effect of the elastic unload on the geometry of the part can be highlighted by using the overlay options between the 2 windows. In gray, the geometry due to the elastic unload, and in blue, we can see then the results obtained at the last forming increment. And here we can notice then the elastic unload You may want to guarantee the mechanical strength of the part of a grain flow that meets a needed specification. In the software, a grain flow fibers marking grid can be used to visualize the grain flow orientation in the section of the part, or to guarantee the specification required in the headed bolts, screws, and studs. Here, the evolution of the grain flow during the wall forming process is present. Then for the several stages, the forward extrusion in 2D, heading, and so on. The marking grid can be defined in the setup or in the analysis mode. Then if you forget to define the marking grid while making the data setup, please note that it is possible to redefine it in the post-processing. For various reasons, some defects can appear randomly on forged parts. Each defect can be detected and analyzed using specific tools in the software. For example, underfilling can be detected by the contact scaler. Faults using the point tracking feature. The piping or the flow-through defect can be detected using underskin marking grid tool or by analyzing the velocity scalars. Cracks can be detected by using several damage criteria. And as we see before, the grain flow can be used to check the mechanical properties. Then in COLDFORM software, we have several features that allow to detect the defects of the screw. In COLDFORM as well, it is possible to model the entire production from forging up to thread rolling. Then I show you before the forming of the screw. Now we will see together the thread rolling operation. Thanks to the precise contact algorithm and the temporal integration scheme, the simulation of the thread rolling is highly accurate. Using a clipping here, or a cutting plane, it is possible to predict accurately the underfilling of the screw thread. This video shows the distribution of the equivalent strain. We can notice the increasing of the equivalent strain in the screw thread zone. If in your application the wire is not annealed prior to forging, please note that you can consider the initial plastic strain. In fact, with our software, it is possible to initialize fields along an axis or a radius. These features allowed the definition of the initial plastic strain deformation along the radius of the billet, as we see in this image in the middle. Then here we initialize the plastic strain. To the right, we have a comparison of the tonnage obtained by the forming of a pre-drawn wire and an annealed wire. For the pre-drawn, we consider the initial plastic deformation as described to the left. Then we consider the initial plastic deformation. By considering this initial plastic deformation, we can notice that the pre-drawn wire have a higher tonnage is required to form it. Use of phosphatized steel reduces wear of the tools and the dies in practice. If your wire has been phosphatized, it is possible to take the phosphatization into account in the software while making the data setup. Here we see how to make it in the interface. Then you need to go to advanced and then phosphate coating and to define an interface set where the phosphatization will be defined. Here in this image, we can see that the surface that is in orange, it is the zone where we define the phosphatization, where the wire is considered as phosphatate. Now we will go to another application. Let's talk about another application, which is the manufacturing of a bolt. This case was provided by Lizzie Automotive Company. The process is done using 5 steps, including a piercing at the end. Then we have stage 1 till the piercing. Between each stage, a transfer step of 0.4 seconds is included. The first stage can be calculated in 2D. This stage is very simple and results are obtained very quickly. As you can see in the second stage, COLDFORM allows to verify the level of the deformation of the part. In the third stage, the simulation will be done in 3D. As you can see, we still have symmetry in the final bolt, so only a part of the bolt will be simulated. In the last stage, before the cutting, it is possible to check the risk of the faults and the design of the tools. To form this bolt, the last stage is a piercing one. Here we present the modeling of this stage. We can check the level of the deformation during this stage and the shape of the part during this step. In this graph, we can see the stress graph that shows a peak at the time of the piercing. Then here we have the stress graph, and we can check then the maximum force needed to create the shearing operation. In the last step, thanks to the improvement of the software on the damage and a new mesh strategy adapted on the damage criteria, it is now possible to obtain a very precise quality on the sheared surface, as we can see in the image here in blue. Then we can see the refinement of the mesh on the sheared surface and how we can predict accurately the sheared surface. Here we have as well a comparison between this numerical results and this is the piece that is obtained by the reality. You may have problems about the die wear, or you are interested in increasing the die life. The die stress analysis is the key that must be studied to increase the die life tooling. For users who have problematic with tools, a die stress analysis can be performed. Major causes of damage in cold forging are the mechanical fatigue and the plastic deformation. Anticipate defects can be benefit for reducing maintenance costs and increasing the productivity. 3 approaches are available to compute and study the stresses in the dies: rigid die approach, uncoupled approach, and coupled approach. Working with rigid die is good for the analysis of the material flow, the forging load, or the properties of the part, for example. But if you are interested in having information related to the dies, such as stresses, you have to work with deformable dies. The advantage of performing a fully coupled die stress analysis is that all interaction between the workpiece and the tooling is at any time step of the computation is calculated. Therefore, temperature, deflection, or stress variation occurring on the dies are accurately modeled. For tools analysis, the main results to look at are the hydrostatic pressure, where the negative values highlight tensile zone and the positive values highlight compression zone. The von Mises stresses value can help to detect plastic deformation. Hoop stress can be used to know the tool force needed for opening. In the next slides, we will see how to model more complex tooling such as shrink-fit dies and multiple inserts. An interface fit, also known as a press fit or friction fit, is a form of fastening between two tight fitting parts that produces a joint which is held together by friction. The use of the outer rings improves the mechanical behavior of the die. In 2D, a coupled approach with deformable dies is used. The ring and the insert are modeled, and the pre-stress is calculated by an interpenetration method. To the right, we see the YY component of the pre-stress tensor at the first increment. Then here we see that since we consider the pre-stress, we have negative value of the hoop stress that shows the die that is near the billet is in compression, and positive values that highlight the fact that the insert is in tension. Several results can be analyzed, such as pressure, von Mises, and the displacement, and the hoop stress. Here we have a comparison between the values of von Mises stress with and without pre-stress. It can be noticed that the values of von Mises with pre-stress is lower, which highlights the effect that the pre-stress state applied on the insert improves the mechanical properties and behavior of the tooling. We saw how to model the pre-stress in 2D. In 3D, the comparison of the pre-stress by the mesh interpenetration method is limited because of the phase discretization problem and the irregular interference fit. Here we see then the phase discretization. It will be difficult between the insert and the ring. For this reason, to consider the press as a virtual interference method called VIF is used in 3D. The concept is to add virtually, then in the surface in pink, to add virtually a pre-stress on this surface and to solve the interpenetration. The main output are the pressure, the radial displacement, the von Mises, and the first and third principal stress. Then on this case, now we will see the result and how to consider the pre-stress. The advantage of using the virtual interference fit is to avoid the modeling of the part, which is then, since we will not model all the parts, we will decrease the computation time to avoid the phase discretization problem that we saw before between the ring and the insert. And we have the possibility as well to consider several rings. For example, here we have ring 1 and ring 2. We can consider several rings and the interpenetration between the different rings. When computing the pre-stress, here, for example, we model the pre-stress in 3D. And here we will analyze the results of this pre-stress by the end of forging. When computing the pre-stress using virtual interference fit, the nodes that are in the vicinity of the billet, they do not move. There is no displacement of the die in the vicinity of the billet. Here we can notice that the displacement of the die near the billet is neglected when considering a pre-stress. And here in this slide, we make a comparison of the von Mises results between two cases, with the pre-stress and without pre-stress. When computing the pre-stress using virtual interference fit, von Mises values are lower. This die is less deformed than this one. And the mechanical behavior of the die is improved. Then now we see together how to use the COLDFORM to make die stress analysis. Then now we will go to another subject, the optimization model. Then if you want to improve the production quality or speed your design phase, the optimization model integrated in COLDFORM is very helpful. In this section, we will present and use this optimization model. The optimization model can be used in several applications, for example, in reverse analysis problem. In order, for example, to determine the friction coefficient, here, for example, we have the ring test to determine the friction coefficient, or, for example, to determine heat transfer coefficient during a quenching. The optimization model can be used to optimize the tool or the billet geometry. And this optimization of the geometry can be in link with the common CAD software. Here in this presentation today, we will present a case of optimization applied on the forming process of a screw. The screw is made by two operations, a preform followed by a heading operation. To the right, we display the temperature evolution obtained after the preform operation. And to the left, the von Mises stress obtained during the heading operation. The aim of the optimization is to get the best filling by modifying the preform results. In this optimization case, the parameters P1 and P2, P1 is the head diameter, P2 is the head height, will be vary in a specific range in the aim that the final screw gets the desired shape and the best filling. The constraint in this case is the die filling. It means the simulation has a good result if it respects the filling of the die cavity. The variation of P1 and P2 was made by Creo. As well, other coupling are possible, for example, with CATIA or SolidWorks. This table presents the initial values of P1 and P2. Parameters are parameters. Then here we have the initial values of P1 and P2. Here we have the values of P1 and P2 for the best individual. The part is in green. The part in green is the best result. Is the result obtained by the best individual. An overlay between the initial simulation and the best individual, we show it is shown here. Then this overlay shows the improvement made by considering the best individual, the improvement of the head filling. To the right, we see the torque obtained for the best and the worst individual. Considering the best individual, we can notice the positive impact on the torque applied by the screwdriver. The design space exploration of production process parameters made by the optimization allows the improvement of the production quality and to speed the design phase. Let's talk about mechanical joining. COLDFORM is a finite element analysis software with robust capabilities to solve simulations with large plastic deformation or multi-bodies. It is possible to model and analyze several mechanical joining processes such as clinching, screwing, then here we see a video of screwing, here we see a video of punch riveting, and here a video of self-piercing riveting. On a self-piercing case, to determine the diassembly force, we make a vertical diassembly test. Here a pull-up tool with a sticking friction behavior is considered. Precision meshing feature is important in order to consider accurately the contact between the parts. On the animation, we visualize the von Mises stress, and on the graph, the needed diassembly force. Fasteners products are widely used where high tensile stress and high fatigue resistance are the main design drivers. To obtain these properties, fasteners are quenched and tempered. SimHeat is our solution for modeling heat treatment. Here we see the forming simulation made in COLDFORM. And the heating operation made in SimHeat to determine the influence of the heat treatment operation on the final mechanical properties. For example, it is possible to determine the hardness, as we see here, after a tempering, or to determine the phase change needed after a quenching. To conclude, we have seen during this presentation that you could create effective simulation of fasteners forming process. The full sequence can be modeled from the wire shearing to forming, then the thread rolling and the mechanical loading. The elastic unload can be identified at the end of the forming. COLDFORM represents a key tool to simulate the production fastening solution. It is easy to design and validate the forging sequence. To predict the workpiece properties, such as shaping, feeling, the internal stresses and the hardness of the part. Using the software, it is possible to make a die stress analysis and to increase die life tuning. It is possible to model the pre-stress due to shrink fit dies and to consider multiple inserts. The optimization model can be used to improve the existing process and the production quality or to speed your design phase. Sim heat can be used to model the heat treatment operations. Now we have reached the end of this webinar. Thank you for your attention.